Okay, and I will try to summarize Albert's CV. I say try because he has such an impressive CV that it's difficult to cover all his achievements. Albert de Roeck is a senior research scientist and staff member at CERN. He's also a professor at the University of Antwerp in Belgium and a visiting professor at the Institute of Particle Physics and Phenomenology in Durham, UK. He obtained his PhD at the University of Antwerp on an experiment at CERN, studying the multiparticle dynamics in hadron-hadron interactions by colliding meson beams on proton and nuclear targets. After his PhD, Albert spent 10 years at the DESI laboratory in Germany, where he and his team made very precise measurements of the quark and gluon structure of the proton. In the late 90s, his interest turned to the possibility to discover new physics, in particular supersymmetry and extra dimensions, and he returned to CERN and joined an experiment at the Large Electron-Positron Collider. During the following years, he played a significant role in the preparation of the CMS experiment at the LHC. Albert has been one of the leaders of the physics program at the CMS experiment. He has had many responsibility positions in the experiment over the years, particularly in the areas of Higgs and exotica beyond the standard model physics. As highlights, he was the deputy spokesperson of CMS in 2010, 2011, and the Higgs convener in 2012, 2013, when the Higgs was discovered. His interest for beyond the standard model physics and exotic signatures, such as long-lived particles, is also evident in his contributions to the Particle Beyond Colliders effort at CERN. Continuing with his interest to search for new things, he's now trying to better understand the neutrinos. Albert is the leader of the CERN EP neutrino group and a member of the Dune and SB collaborations. In Dune, he works on searches beyond the standard model. In particular, he is responsible for the heavy neutral lepton working group and has been editor of the Dune physics technical design report. So Albert, it's a great honor to have you here, and you can start sharing your screen.
All right, it's a great pleasure for me to be there. In fact, I would have preferred to be there in person in Madrid. I always enjoyed to be there. But this is probably the next best thing we can do, and that's how it's gonna go. So I'm gonna cut actually my video, so you have here a chance to see me for a moment. But because it's better, I think, for the bandwidth from where I started, that it doesn't get interrupted. Okay, so I'll now go to the sharing part. Get up this. And now you should be okay seeing the slides. If not, please tell me. So yes, thanks for this invitation. As call it in the context of what was just told, a new hobby, which I have, and I never see it as a real job, but as a hobby, is now looking for beyond the standard model physics, which is something I've been desperately looking for years, and still do, by the way, also at the LHC, and trying to use the opportunities that actually are getting presented by the fact that we're going to have very precise neutrino experiments, and which can be used for that. So I will be talking about beyond the standard model physics with Dune. Now, just to put everybody on the same page, this is how Dune, or the LNBF, the accelerator part, and the Dune, the Deep Underground Neutrino Experiment, will consist of. There will be a beam, for those who are familiar with high intensity beams. It's a 1.2 megawatts upgradable beam of 60 to 120 GeV protons, which create neutrinos, which are, of course, of lower energy, as you will see. And they go from Chicago, from Fermilab, so not from CERN. This is, by the way, one of the first experiments that CERN is actually participating, which are not on the CERN side. But this is a project shooting the neutrino beam 1,300 kilometers from Chicago through the Earth to a mine in South Dakota, and where big detectors will be waiting to see these neutrinos. There is going to be a near detector, which is a purely detector measuring the rate of neutrinos going there before we expect them to be oscillated, at least in the standard neutrinos which we have. And that will be mostly muon neutrinos going there from pion decays. But on the way, there will be oscillations as expected. And as we know now from the experiments we did so far, we will measure here muon neutrinos or electron neutrinos, or even sometimes tau neutrinos, although they need to have enough energy to be measurable. Dune, for people working at the collider, as myself, also in part-time, Dune is a kind of a global collaboration of a size similar to a good collider experiment, not quite yet as big as Atlas and CMS, but certainly competitive with ALICE or LHCb, for example. It's a bit bigger even. You see here is about, well, almost more than 1,200 collaborators signed in as in October 2020, and they come from 180 institutes and then 31 countries, plus CERN. And still more groups are joining. And I like to show this picture below here because once a year I have the pleasure of organizing a Dune week or a Dune collaboration week, which is actually at CERN, partially because we do quite a bit for Dune at CERN itself with the protodunes, which I will mention in a moment. But also people like to come to CERN. And compared to Fermilab, apparently we have a good reputation of being maybe perhaps a bit more pleasant environment for also socializing and things to go to. Well, that's me who said it. Don't take it too seriously. Anyway, a collaboration meeting at CERN, for example, and mind you, this is an external experiment, still gathers something like 350 participants. So it's like a small conference, if you like. And this was the last picture we took, and then COVID was happening. And this year, next year, we're not going to have it in January at CERN for obvious reasons. But that is the last time actually these people met in a collaborative environment. This is Dune. Dune has FAR detectors, as I said, in the South Dakota mine, which is the old, it's now called Sanford. It was the old homestake mine for those who know about the solar neutrino measurements and so forth. And I will go a little bit more in detail what exactly this FAR detector is, as well as the near detector. Two big things are special with Dune. This is the FAR detector is kind of a very precise detector, not just a water tank or so, but it's the liquid argon TPC, and I'll show that a little bit further. And the near detector is very sophisticated. In fact, it's a collection of 3 detectors, and we'll have a look at that also in a moment, but this gives sort of like a wrap-up of what is in there with these detectors. To get an idea when the whole thing gets started, these are the official milestones. They are for the forward detector. So the excavation should be beginning next week next year, well, which is almost next week, but a bit more. And the first detector, there will be 4 detectors, FAR detectors. The first detector will start to be installed in 2024. So not too far away. And 2026, this detector should be ready because it's a big volume of liquid argon, as you will see. So that's the FAR detector. In total, we will have a 40 kiloton roundabout fiducial liquid argon time projection chamber volume. And they are installed as 4 individual detectors of 10 kiloton each. In fact, there are 17 kiloton, but the fiducial volume is 10 kilotons. And they are about 5,000 feet under the surface, which means 1.5 kilometer deep. So you see a bit here the structure, where they are and where these detectors are going to be. We use liquid argon. Why do we do that? Because we want to have a good target, a dense target, then for the neutrinos to interact with, as they act very feebly, and it's about 40% more dense than water. It's actually cheap liquid argon. You might not realize that, but in fact, 1% of the air you breathe has argon in it, argon gas, so you get it out of the air, and it's not a very expensive thing to have. It's easily ionizable, so it gets good signals, and it has excellent photoscintillation. So if you put photon detectors, you can also see the light propagation of that. And this is the temperature of argon is like the one of liquid nitrogen. So you can do tricks like that and pouring some liquid argon, which is actually colorless liquid argon, if you look at it. That's the FAR detector. That's one module of a FAR detector. It's a big cryostat within there, the time projection chamber. So the time projection chamber for the one we're going to build is going to be what they call the single phase detector. It will be, everything will be in the cold, and it gives some details of that. Oops, click back on this, we're going back. You will just have a drift. It works like a TPC in gas, except it's in a liquid. So you have a 3D type of interpretation of things when you measure the points as they project onto a readout plane, like in a normal TPC, and you measure the time also for the drift that it took for these electrons to get to this readout plane to get the third coordinate. And well, there are two very big challenges, I think, with an experiment like this. Is this actually to build liquid argon TPC with the stability and purity of the level and the size that is needed? It was maybe not fully set here. Well, okay, this is something like 50 meters long and 16 meters high, and it's quite a big experiment. This is a module, a part of it. It's a 4% of such a detector, which is the protodune, which we built at CERN. And this we have tested, filled with liquid argon and measured. And here you see a collision actually from a pion beam coming in and creating this kind of picture. This is what you see in a liquid argon TPC. And combined with also the photon readout, which you don't see on this picture here, this is just the tracks from the ionization, you can get actually both tracking and an excellent calorimetry by such a detector. You can have low thresholds here because you see these things, because you get really capabilities of what I would call a modern an electronic modern bubble chamber. You know, bubble chambers, I made my PhD thesis still on one of the last bubble chambers experiments at CERN, so I appreciate what they could do. And this is a really kind of an electronic version of that. So it's a very capable detector. The quality will be high. Good, that's the start of the neutrinos which are being created. As you see, you have this 120 GeV beam going on a target, and that will lead to pions, which will decay into muons and neutrinos. And the neutrino spectrum that is coming out of there typically is in a few GeV range. And here are a few parameters which will impress people that know high intensity sources, because it's a really high intensity source you create. So the more protons you have on target, basically, the more neutrinos you're going to get. These neutrinos are then sent on their way, and they pass one point, which is the near detector, which is about 500 meters away from the target and from the decay tunnel where you get the neutrino being created. And that near detector is also quite special for Dune, is that it's a set of very capable precision detectors. Now we're still at the phase of a reference design to put them together, so it's not even a technical design yet, but we're moving closer. But this is the idea of what people want to build. First, there will be a module. Well, what is the purpose of the near detector? That should calibrate actually the flux of the neutrinos that are going towards the FAR detector, so that you can look there in the FAR detector and see if your neutrino, muon neutrinos have disappeared, or antineutrinos. We have the two types of beams. And, or of course, if electron neutrinos appear, which you can measure directly, but you can calibrate how much what you would expect there, and then that allows you to measure precise oscillation parameters. So the near detector is going to be very instrumental for the BSM physics, which I'm going to discuss. And so I'm showing it a little in detail. It has, in fact, 3 detectors, one following the other. So the neutrino beam comes this way. There is first a small module like what we had in this protodune of liquid argon going to be in front of here, because you want to have collisions the same as what you would get in the FAR detector, although in detail the detector is somewhat different, but it's a liquid argon target detector. Then you want to understand the liquid argon interactions and how you classify them, and what you may be missing, and understand the nuclear aspect of these things. For that, we have a gas detector followed with liquid argon, but under high pressure. And then there is another detector here, which actually going to monitor the basically the flux as they go through of the neutrinos you see. Because these two detectors are going to be actually able to move off axis. They're going to move away, sort of like perpendicularly to the beam coming. That has all kinds of interesting features. I will not go so much to that, but we can make use of that also for looking for BSM physics. The next 3 slides I will not go in detail to, because that is for you if you wish to look at how such these near detectors really look for. For example, the liquid argon detector will be 60 tons of fiducial volume of liquid argon in here, but in a modular structure. And then because the neutrino interactions, we're going to actually get so close to the source will be so high, we can even have pileup, and therefore, which is very well known in the LHC experiments. And therefore, we have a modular structure with much smaller drift times than we're going to have in the big detector, but the same target. The gas detector is given here. It's a big volume. It will be, well, this one will be not in a magnet. That is difficult to handle and would create problems, because also the far detector is not in a magnet. But the intermediate detector here, which is on a gas to measure particularly properties of collisions of neutrinos on argon in detail with very good resolution, that will be in a magnetic field. And we can then also make more differential studies for that. And then the far detector, which is going to be mostly plastic cubes surrounded by some tracking detectors, like maybe normal cast TPCs. And for the plastic cubes, I just say this is one of the things we are developing at CERN. You see here small cubes, which are going to be able to see signals from these detectors coming read out by these optical fibers here. They are 1 by 1 by 1 centimeter. And this volume, which is awaiting for the neutrinos to come, will be about 10 million of these small cubes. So at CERN, actually, we developed something now that we might be printing these, and if the qualities work out all right, as they seem to do, and then this could be the first neutrino detector, which I will actually come from the printer with 3D printing, which is kind of cute. Now the physics, the main program of physics for Dune is a precise study of the neutrino oscillations and measuring interesting variables, like, for example, what is the amount of CP violation that happens there? It's clearly non-zero. We seem to see from experiments already now. How big is it? Can it explain the matter-antimatter symmetry in the universe? That's one of the main questions we have. But also, for understanding where neutrinos get their masses from, we have to actually understand how the mass structure is of the neutrinos. We measure that through the oscillation parameters. That's through the so-called PMNS matrix measurements, and determining the ordering of the sizes of the masses, because we in fact measure only mass differences and not absolute masses. But the detector, the far-away detector which you saw, is quite big and so precise that one of the things we certainly hope for is that some supernova would care to go off during the time that this detector is active, because it will be the most precise detector available since we start building such kind of bit detectors to measure characteristics of supernovae. And also, you have a lot of protons in the argon, which is sitting there, so we can watch them closely. And thanks to the low thresholds we have in that detector, it's also a very sensitive detector, for example, to look for proton decays, which is some kind of a way of new physics already. But for the BSM or beyond standard model physics opportunities, I want to stress that the main characteristics are we have an intense proton source. It's at the high intensity frontier. So we have enormous amount of collisions of protons on target. They can produce things, as I will show. And we have now 2 sorts of detectors also available, a far-away detector and a near detector. And the near detector, particularly close to that source, is like you have for what people classically call the beam dump experiment. And beam dump experiments gained quite a bit of interest in the last years again for looking for low mass new physics. And that is the opportunities I will come back most in this discussion here. And I will, for example, discuss, yep, I have that, searches for light dark matter, which can happen in this environment, and searches for what we call heavy neutral leptons. And I will explain what that is. Axion searches, and something else, which is a favorite of mine, is searches for new charged particles, such as millicharges. So these are opportunities which present themselves thanks to these conditions we start from, particularly the high quality of detectors we have and the high intensity of the source. This is not a precedent. In fact, neutrino experiments already now coupled to look apart from their normal neutrino program to use their detectors for looking for new physics. And I'll show a few examples of real data on the way. So what did happen and what is most, but not all, what I will show based on is the physics DDR, which we completed in the beginning of the year. And out of that, we extracted out of the chapters which discuss new physics, a paper which is on the archive since August or so, which is the prospects of beyond standard model physics for the Deep Underground Neutrino Experiment. This was not a topic very popular at the time. We started like 2 to 3 years ago on that, but it gained interest, and also in fact some other experiments started to do that in the present neutrino slew of experiments. And here's just some list of content of topics which are in that paper, and some of them, not all of them, I will describe. By the way, I'm sure I've found too much to describe in this one talk, so I will actually gloss over some of the physics opportunities, just showing this is being addressed without discussing that in detail. But if you have questions, you can go back to the slide and see, or ask me questions later. There are some meetings are actually focusing on that, and one we had in Texas, Arlington, in year when we could still travel last year. So there was a group of people who have presented a white paper on these kind of opportunities, which I will talk about. We even have a new workshop planned in February on that. It will be probably online. And well, let's say it's surely online. I mean, the US is certainly not in a position that they're going to open anytime soon. And that was meant for the SNOMAS 21 process that started this year, where as a result of that input, they created a group in the neutrino facilities, Neutrino Facility 03 group is called, which is particularly on BSM physics. And you see the mandate here and the people who are involved in this group as convening it. And there were a lot of projects proposed to be discussed in that group, 147 in fact, of which there were, by the group conveners, 32 primary selected and 115 as secondary. If you want more information, you can go to these web pages and see some of the meetings we had on that. But okay, let's come to the main thing of the talk is on searching for new physics. Now, there are 3 ways of searching for new physics with the Dune experiment. That is, first, you're going to look into the area of the oscillation path here, and particularly the fact that these neutrinos go through the Earth may create so-called matter effects, which can lead to beyond standard model physics you see. Then you can go purely to the near detector, which is the bulk of what I'm going to show. And also you can purely, here you use both, by the way, and both the near and the far detector, but you can go purely to the near detector, look for things, and you can go to the far detector where you look for things which are not really then coming from the neutrino beam, but more coming from the sky. The fact that you have a very large detector over here, which is well covered against cosmic radiation, which can use. So, as I said, I'm not going to spend a lot of time on this, but I just would like you to get a few key messages away from this. And that is, for example, one of the topics which is ever coming back still to us, and which is still a bit of an enigma, if they exist or not, is so-called sterile neutrinos. And I think particularly on sterile neutrinos in the electron volt mass range here, which were, let's say, getting popular thanks to the LSND experiment, the electron neutrino charge current excess they had in that experiment seen quite some years ago, and reactor experiments that saw some of the anti-electron neutrinos which are produced coming out of the reactor being less than what they had calculated, and also some other things in the gallium, so-called gallium anomaly. But they all led that maybe there is something like a sterile neutrino around, which would be a neutrino which is not active. It means it doesn't couple to the Z boson, but you only see it really through mixing with the 3 neutrino states which we know of. So it's a new kind of neutrino, fourth neutrino if you wish. And you will be in a very good position to, depending on what the mass is of this neutrino, is it in the fraction of EeV range, or is it in the several of EV squared range, as to say, the mass difference between the neutrinos, the active ones and the sterile ones, because an oscillation of one neutrino in the other is given by the length over the energy of the neutrinos, which is the key parameter, starting to say where oscillations happen. So here you see the energy range which the near and the far detectors are susceptible to, which is the same, but they are at a different L over E range. And you see, depending on the mass, you can start to see deviations from the 3 neutrino paradigm, which you expect in oscillations in these faraway detectors or the near detectors. That you can use and then see if you see signatures for whatever could be compatible with such a fourth neutrino, and look at the possible fourth neutrino mass difference or effective angle plane, you say. And these are experiments done now before, and then you see the lines of the existing experiments. This is what Dune could add to it if it uses its full capacitance and in the best of possible connection of using all the systematics in there. So it will cover quite a big range. I mean, it should be really, if it is not decided by then Dune will actually referee if this is a real effect or not. Now, this is measured as an effective angle here, which is the combination of two elements of the unitarity matrix of the PMNS matrix. You can measure it directly in some angles, θ14, which is the lightest or the first mass neutrino to the second mass, the fourth new mass state neutrino, the second, and so forth. I'm showing this as an accumulation of studies done, but just to bring out that, in fact, there was something interesting this summer. Namely, there was a reactor neutrino experiment that actually claims an observation, a positive observation of seeing an oscillation of the electron antineutrino beam coming out of stream, I would say, coming out of the reactor. I should say it's still controversial. The jury is still out. Their positive signal is sitting here, a bit at borderlines where the other experiments end up or so, but that would be totally into the area where Dune is going to measure. So it may be interesting to see if this indeed, is surviving the test of time. Then in fact, Dune should be making great measurements there of this new type of neutrino. Personally, I don't believe it too much yet, but we will see. We can look at non-standard neutrino interactions. That is, you have the normal matrix of mixing, but you can get corrections to that because some things happen, particularly when the neutrinos go through the Earth from the source through the far detector, and they see the matter around them, basically the UD and D quarks and the electrons, and different neutrino species act differently. And if you have new physics in that area, you're going to see corrections to what you would expect this normal calculation would give for these matter effects to what you're actually going to measure. And you're going to see that in the oscillations. And the main message I want to give here, without going to details, that Dune would be able to go to a factor to 2 to 5 better in precision in actually searching for such non-standard neutrino interactions. Even CP violation or CPT violation you can study in the neutrinos by looking at the oscillations differently how they behave for neutrinos and antineutrinos. And there would be differences, for example, in the mass differences you derive from such a study, or in the mixing angles you derive for such a study for the neutrino and the antineutrino sector. These are current bounds. Dune will actually make a large improvement on these by the fact that it has these precision measurements, and here it is given for those who are interested in the level of precision that could be reached to search for these new effects. But the near detector, that is what interests me most. And what you can do there? Well, you can use this detector here actually to see a stream of objects coming through, neutrinos first of all, but other things that could be created in the target here, which could be maybe axions, light dark matter, or things like that. I will show that. This is a classical measurement. This is measuring just so-called trident events. This is neutrino scattering by exchange of a Z here, neutral current. We see a muon pair coming out, which comes out from the nucleus here, from a photon emitted through this diagram. And you can make very precise predictions for this in the standard model. Now, if you have something extra in the standard model, and this would have to be a rather light Z prime with a special symmetry as given here, an L mu minus L tau symmetry, you can get deviations, and that is what you can measure. And I'll focus only on this slide here, because that gives you what you could measure from measuring these things and comparing with the standard model and to what you expect from these models on eventual sensitivity to such a new Z prime, and the coupling which is involved in there, which is coming here. And the interest in that is that the so-called G-2 anomaly, which is still not quite understood, and of course we're all waiting for the Fermilab experiment now to come out with their number and see if there is still an anomaly or not. But if that anomaly would be there, that has a preferred region in this plane of parameter space for this particular model, which is kind of a general model, but it's peculiar in this, it's in the wave's configuration here, which lies here, which is not covered presently by the experiment. So Dune would cut in there quite a bit with first 6 years of running. And by the way, of course, Dune should run for like 20 years or so with an increasing luminosity as we have for the LHC. But this is what I really find interesting, that you can have protons, which is very large amount of protons, compared, for example, what an experimental ship has, an enormous amount of protons on target. This is lower energy than ship, I should say. They have 400 GeV, but this is 120 GeV at most. But you go through a dump, and in that dump, you can create all kinds of things. You can create heavy neutral leptons, if they exist, dark photons, if they exist, dark scalars, light dark matter. This is what is the opportunity, I think, which is more and more realized now and brought forward, particularly in this group, which I said is SNOMAS. You have a near detector, which is a few hundred meters away from this point where you create these things. So either you can create some kind of stable particles, which are weakly interacting typically, but they can interact with your detector. Or, like for example, for the HNLs, you can create long-lived particles, and they live long-lived enough that a good fraction will actually decay in that detector. These are the two kind of cases we have. Good. I'm not going to insult you by telling that we are all still a bit excited about this dark matter in the universe, which we still don't fully understand what it is, but that is just for a summary of signatures that we have. You know, dark matter, if it is there and if it is a part, it really interacts only through gravitation as far as we know. And there are many experiments, direct and indirect search experiment. The collider also contributed to that, searching for dark matter. They're sitting most in the GeV to 100 GeV to TeV range for two reasons. First, that is where the so-called WIMP, the weakly interacting massive particle paradigm, is working, and that is, you know, has been, or for a long time, and maybe still is, our best bet that such a particle could be. But no evidence has been found so far. This searches for these detectors, particularly the direct experiments, gets less and less as you go to lower masses, because they are based on a recoil, and the recoil you have of a dark matter particle in your experiment with a low mass dark matter particle is going to be less visible. You're going to see that with much less efficiency or no efficiency at all in some experiments. And therefore, these experiments are not very sensitive to lighter dark matter than, say, of the order of a GeV or so, or that area. That would also not really be WIMPs in the classical sense that we said. They may be still weakly interacting particle, but as a WIMP, one thinks mostly as a thermalized distribution that comes out from its cross-section and its interaction. In fact, if they are so light, they would overclose the universe. So they come out of dark matter models, which are a bit more evolved, and think on having not just light dark matter particles, which is weakly interacting, but also having light new mediators around there as well, like dark photons, ALPs, and so forth. That got popular by itself, because also at the LHC, for example, there is now the phaser experiment, which is particularly going to look for these. Anyway, how do we produce these dark matter particles? Well, they are basically produced in the, if they exist, always to say, in decays of mesons. And if we have one thing a lot at a beam dump or a neutrino beam experiment, there's a lot of mesons being produced. And even a fraction decaying on that, maybe 1 in a million or a trillion or so, can still give you a significant amount of dark matter particles created in the process. And that is not new for Dune. For example, Mini Dune a few years back, did I put the reference? I didn't put the reference, but it's 2 years back, I think, made already such an exercise. They have an 8 GeV beam, not as intense as what we'll get for Dune, but they use the pions, which normally decay into a muon and a neutrino, but you could also have, like, for example, a pi 0 decaying into something which is this intermediate particle, this mediator, which I was talking about for light dark matter, and they go to dark matter particles. So instead of pion gamma gamma, you have pion gamma A, for example, which stands for this particle you have here. And that particle would then go through, dark matter particle, go through the over of the Earth to the detector, in this case the mini boon detector, and could create a scattering in there. And what was found is that, in fact, they get competitive results to what was already available. Maybe you're not entirely impressed by the increase here of phase space covered by this experiment, but this was a new approach for looking for this. Well, I will probably skip this for time, but such searches we can also do at Dune. And in fact, at Dune, you get this kind of sensitivities for light dark matter produced in pions and etas in the beam dump, where you, instead of neutrinos, create now this a small fraction of the time, and you have dark matter coming in, and you measure the dark matter particle scattering through exchange of, again, of this mediator here with the electrons, and you see actually like a neutral current interaction where you would see suddenly an electron kicking out of that. And that is what you go for, and you see for in the parameter space of such dark matter models, these are typical parameters which we have, you see the range that could be covered. I only mention here that we are normally having this detector on axis, but I said some part of the time we will use this detector off axis, and that is even giving you a better sensitivity for the simple reason that the most of the background is neutrinos, but the neutrinos are really directed through the decays of the pions, and by decaying the charged pions to the near detector straightforward. I mean, not to the near detector, the far detector, in fact. And if you move near detector to the side, you can have more sensitivity to the neutrals, which you did not control with this magnetic system. All right, now heavy neutron leptons. This I think is a very nice possible extension of the standard model. Sometimes I compare it on par with something like supersymmetry in trying to explain in a simple way many things at the same time. What this heavy neutral leptons could do. What is a heavy neutral lepton? Well, by definition, it is a neutrino, but it's a sterile neutrino, but not the sterile neutrinos I gave you from before, which we looked at, because these are neutrinos more in the mass around the GeV, and they could be even higher. They could be tens of GeV. In fact, we also look for these at the LHC. And what are they? They are actually the idea that you have the standard model, as you see here. And if my mouse comes back, yeah, here we go. This is the standard model, all the particles we know, but this is presented in a way that you also see that there is a left-handed and a right-handed, or a left chiral and a right-handed chiral particle in there. So for all the particles, we have left and right-handed chiral states. We do not have that for the neutrinos in the standard model as we have it today. This looks like there may be partners missing here. And that is what this neutrino Mssm model aims for. It says, well, there are three partners missing, the N1, N2, N3, by lack of a more inspiring name. And these 2, N2, N3 are going to be in the maybe 100 MeV to several GeV, or maybe even tens of GeV range. These are sterile, these are singlets with respect to the interactions. And the N1 maybe is in the KeV range. And what that would then mean is that this N1 could be stable or semi-stable, giving a good dark matter candidate. And this fact of the judicious choice of where the N2s and N3s are will give you a mechanism to actually, through the seesaw mechanism, give mass to the neutrinos, so it will solve that puzzle. And it can explain also the baryon asymmetry through the properties it have here. So you will catch three stones, or you catch three birds with one stone with this type of model. So in that sense, it's sort of like a minimal model to try to explain many things. Now, of course, these things have to exist if that were true. So we look for them. And looking for them means looking for these kind of new type of neutrinos, which have the property that they actually decay. They are not going to decay. The N2 and N3, they are actually not stable states. They are going to decay. First, you need to produce them. You produce them, for example, as you produce normal neutrinos, when, for example, a ds decay here, and I say that because this can go to high mass, and that new neutrino can mix and become an N2 or an N3. Same in this diagram, the N2 and N3 then goes on and decays back to states like this. And for example, this is a very exotic state you would easily try to see. What's interesting about this is that it depends on how the coupling goes between the neutrinos, which we know, and these heavy new neutrinos, how small it is basically, and the mass of these heavy new neutrinos. This goes via a certain lifetime. And the lifetime can be 10 centimeter, it's meters here, sorry, 10 meters here, 10 centimeter, and so on. So these are kind of prompt decays. We will not see that in these neutrino experiment detectors, but these are ones which can go over meters, tens of meters, hundreds of meters, kilometers even. And this corner, you can actually search for the low mass things. And particularly from a D quark, you get at maximum something like a 2 GeV neutrino out of that. Again, has been done already for some experiments. Just recently, you see, these are papers from last year, where the microboon and T2K experiments, they have a lower energy. They could only look at kaon decays, basically. And then the conversion of this signal they look at in detector gave some first limits, which is not so bad. This is couplings at 10 to the minus 7. But we want more. Where do we want to go? Well, maybe like 10 to the minus 10 or so. And that's one paper from last year, which is just a phenomenological study, what the range could be for finding these heavy neutral leptons. It had some preliminary input. It was good, but it had a preliminary input. We do better. Now, Okay, no, first before that, I show where that looks, where everybody else is looking. So here would be the sensitivity of Dune going here, right up. Oh, maybe I have even something. Yeah, I have that. Compared to other future projects, like possibly a Methuselah detector at the LHC, the SHIP project at the beam dump experiment for CERN, for example. And you see we're in the same range. Here, the other ones win because they have higher masses, and they can go to high mass resonances. But in this range, we are quite good. And if neither SHIP of Methuselah happens, then Dune will be the best thing in town to cover this region here. That, again, to save a bit of time, this is what we did recently in our study for the conceptual design report of the near detector. And we looked at more channels and looked at updated neutrino fluxes. And you see that now we actually fill in this whole range here up to the seesaw limit. Here you shouldn't live, because then the seesaw mechanism doesn't work. Here you are a bit in conflict with the Big Bang nucleosynthesis, but that is dynamic. This is a very hard limit here. And what theorists typically like to see is that we can cover this part here. And we should be able to do that up to 500 MeV or so, and have not a very bad measurement here, particularly if SHIP would not happen very soon, which actually seems to be the case right now. We have a whole program on that. We have a working group on that. It was already mentioned that I was involved in this. If people are interested, there is lots of things to be done still to study minimal, non-minimal type of processes. We will do that for SNOWMAS, and we will do that for Dune. This is just an advertising slogan for interested people. All right, let's see. Okay, maybe I have another 10 minutes or so. Another type of particle, which I find particularly interesting also, is, and that also came up in the last year, maybe 2 years, for looking at in more detail at this neutrino experiments, is for particles that have a fractional charge. They have a charge which is less than the electron charge. And that actually started from some activity I had at the LHC for an experiment that I will show a bit later. But this sort of revived this idea. This is an old idea, actually. It's an idea that maybe there is a dark QED sector. So maybe in the dark matter world, there is dark QED happening. And if dark QED would be happening by exchanging a dark photon, like we exchange a normal photon in the normal world here, and that dark photon happens to be having zero mass, which is not in all the dark photon models, most have some mass, then you naturally need to get particles that would couple to this dark photon, which we would see in our world as particles which have a fractional charge. Besides that model-driven interest, say, in finding millicharges, there is generically the question, do particles exist that have a fractional charge compared to the electron? And I'm not talking really about the quarks here or so, but really much smaller charge, and maybe 1/1000th of an electron charge or so. And there are connections with the dark sector as well. In fact, in some areas you can think that perhaps you need such kind of dark sector, dark component with the normal dark matter that we have, which has a fractional charge, maybe like 5 to 10% or so, which has been claimed that you might want to have in order to explain the anomalies seen in the absorption lines of the 21 centimeter spectrum in edges. I will not give details on that, but we can discuss later if you want. Anyway, how do you produce these millicharge particles? Well, again, in meson decays. And particularly, for example, pi zeros, etas could go to a normal photon and a virtual photon, and the virtual photon, just by charge, can couple to these guys here. And there is some branching ratio allowable for that, as you see. Well, there is also Drell-Yan, but that's mostly for the collider that works. That's not so much for the neutrino experiments. And you see that in the branching ratios, which we have for a pi zero going here, there is already that channel allowed. This goes via this virtual gamma star. And the fraction you would get of pi zeros doing that would be exactly this fraction multiplied by the square, the charge squared of these millicharges. So if they have a millicharge of 1%, you would reduce this branching ratio by a factor of 10,000. How do you see them? Well, such a particle can scatter through normal photon emission and or exchange, I would say, with an electron. And again, you see something like a neutral current interaction, like for the dark matter diagram we had before, depending now the coupling totally driven by the charge of that millicharge particles. And these are the scatter experiments you could use for that. The rate is high. Typically, we get something like for 1 year of running, we would get something like 10 to the 14 to 16 or so of these channels produced, and then you have to wait with the charge squared to weight it down to see how many events you actually would be seeing that could be the millicharge events. That gives search possibilities, as you see here. So they have been searchable before, particularly in the 90s and so on. Then people have not drawn much attention to that now, but due to the revived interest, this is where you could go with different experiments. Here's the Dune experiment, for example, the sensitivity, what they could cover, and you see the contributing sources of these millicharges that in their decay of these particles could come there, and this is what we have. This is, by the way, an experiment, Millikan, which is it's proposed as an adjoint experiment for the CMS detector, which actually started for me this interest in all this thing. In fact, already it has been tried out last year with data which was available from a detector, a liquid argon detector, which was in neutrino beam, a small one, 200 liters only. And they looking for scatterings of such possible particle with electrons, leaving some like small electron blobs coming out here. And they align them to the target and see if there is anything found. They didn't find anything, but they had already quite an interesting exclusion limit from this experiment. Well, I won't have time for this, but we search for that also at the LHC, and this is a group of people doing that. We do that with scintillators, and we look for actually particles going through there which give very, very little light, close to 1 photon per scintillating photon per detector. And that, since we produced our results and we have a first paper on that, there are many ideas that popped up saying, oh, we want to have something like that too. And they're thinking of that, just to give you some idea that it's a popular thing. And even a week ago, somebody went to the big European bubble chamber data from the year of 1982. He digged out, he didn't go and look at the pictures because we're two theorists doing that, but they used the data which came from a 400 GeV beam dump run, looking for these scatters in the BEPS, and they could produce actually a new limit using these data 40 years after they were taken or so on millicharge particles, just last week. The final thing in here, I'll say, is axion particles. That also gains a lot of interest since we don't find WIMPs as the possible dark matter candidates. Axions has always been something to look at next. Now, the true QCD axion is very light. This is not what we're talking about. It's not an EEV axion-like, but an axion particle. But it's an axion-like, meaning a pseudoscalar with a similar type of coupling as for axions. And that's produced either through just photon conversion from photons, which you can have from pi zeros, for example, which can convert into an axion through the Primakov effect, or for quantum scattering type of electrons and photons, where you can get this axion through the coupling if they exist. Detection, then, you look for suddenly photons in your detector, which come from an axion going to the inverse process, or an axion in some region of the phase space can actually decay. And the first study shows that indeed the Dune experiments, even with a year of data or something like this 10 years of data is gonna cover new region for axion experiments or axion search. Okay, this gives an idea what we can do. There are more to be said. I will not go to that. I will say in 2 minutes only, because I'm running out of time here, that you can also do BSM at the far detectors. And that has also triggered my interest, for example, for looking for special cases of dark matter in there, which you could see. These big detectors are not like a direct dark matter experiment. You have to have a much better purity for seeing the recoils of dark matter experiments as they would have. In fact, Lux experiment is sitting next door to where the Sanford thing is, so they do that job. What these detectors can do is actually looking for more energetic dark matter, even if it's light, but it's more energetic coming in the detector. And that comes to typical ideas of relativistic dark matter. That needs to assume that dark matter is not just one particle, but there are several of them. There is a heavy one, which is making out the dark matter on the gravitational level as we see, and probably does not interact with us because we haven't found it interacting with us. But there are lower energetic ones, and they can actually interact with us. And annihilation of the heavier ones can lead to the lower mass ones, but they interact with the standard model, so they will not stay along long. This will be the dark matter, which we see as a stable dark matter here. This will be temporarily created through these annihilations, but they can interact. But they come in, they are light, maybe 10 MeV or so, but they come in maybe GeVs of energies, and therefore they can be seen and detected. And we have special cases like that. For example, that's one I worked on with some theorists, when there are in fact 3 species, when you have this election, and then during the interaction, the lighter one gets upscattered to a secondary light one, not to the heavier one. This is the very heavy one, and that can lead to an additional signature. And signatures like that, for example, can be looked for, and then you see what you can cover extra in parameter space given on the starting conditions. So here the heavy guy is 2 GeV, the lighter guy is 50 MeV, and the one but lightest guy is 60 MeV. And you see what you can cover for the different scenario. The final thing I show on this here is that people think maybe the sun is an accumulation of, in such kind of boosted model, creating annihilations of dark matter that is sitting in the sun, is absorbed there, is trapped in the sun, and the density gets so high that this heavier dark matter states start annihilating, produce the lighter ones. They are ejected from the sun because they have a boost, they have energy, they can react with our detector, and we can look at that. And of course, in that case, if the sun is the source, we can actually point the events we might see in the liquid argon of dark matter interacting with the argon atoms, this direction with the direction of the sun to reduce the background. And well, one gets some interesting extensions of the possible limits we have today. Okay, well, if you want, we can also use these dark matter experiments as surface experiments, which we have already now, but I will not go into that here. So, apart from these things, yes, we can look for baryon decays or neutron oscillations, and these are interesting numbers which are here, but you may have seen this already because they are around since about a year or so. There are ideas of optimizing the detectors. Now we are just using the facility as there is and as we see it, but there are ideas around for some future to have an optimized dark matter beam, if you wish, by Julius magnets and focus horn focusing. I will not go into that, just to say it exists, and maybe I conclude. So BSM physics at the neutrino facilities has been receiving growing attention. I gave you a taste of that. There is more to be seen in the paper I gave or on the workshops I alluded to a little bit, particularly on the things I like, of course. The Dune experiment can provide great opportunities to search for and study BSM signatures such as light or boosted dark matter. And this is using the experiment as is, not actually changing it particularly to optimize it even better. That could be something else one can think of, but that is not part of the main program at this point. So at this moment, we are opportunists to use that. So I showed some things related to the neutrino oscillations themselves. But then particularly I showed to what the beam-induced new phenomena can do working with the near detector. And these are a few examples. And I went very quickly over some cosmic originated things we could do with the forward detector. And if we put the slide somewhere, you can always look at that. But there is an increasing active collaboration between experimentalists and theorists, phenomenologists. Even this morning, I got a theorist contacting me with a paper on some new ideas he had. So, no, these are very welcome. We have the mechanisms in place. We have workshops, a workshop, which we have from time to time, and we have the Snow Mass Forum to discuss that. But I would say is that with what we are planning to build and what we are, of course, monitoring from our BSM side is that Dune will be very well prepared for observing more possible surprise in the neutrino and the BSM sector if it happens that BSM physics is indeed in the area like I discussed for. And I think I'll stop here. Thank you.
Thank you very much for the wonderful talk. We have time for a few questions. You can raise your hand if you want, as usual. Ines?
Yes, can you hear me?
Yes.
I hear you.
Okay. So Albert, thanks a lot for this fantastic talk. I think this is a super nice example of the physics topics that are in synergy with colliders and LHC. And in groups like CIEMAT, I think this is important to have to search for new physics from different perspectives and different detectors and possibilities. So I have one comment regarding the dark matter searches in the FAR detector. I think I know you know that there are still current efforts in order to improve the future modules of the FAR detector of Dune to be able to extend our physics reach, not only for the dark matter searches, trying to improve the background conditions, the purity, and to optimize the detector, but also in general to optimize our reach on low energy physics. So, and there is a workshop that is being organized next week with this precisely topic. And related to that, my question was on the topic of the heavy neutral lepton, which I think is one of the favorite ones here at CIEMAT. People are working in neutrinos, we understand the model. I wanted to understand really the limitations that we have now to extend our coverage, or is it really limited by the beam? As you said, we are using what we have right now, but what else we can do in order to improve that search? From the detector point of view, is this something that we can do in order to, I mean, is precision important? Is the mass, or is really mainly focused on the optimization of the beam?
Yeah, sure. One thing is the energy of the beam. The energy of the beam is 120 GeV maximum, what we have, the proton beam. And that makes, if you look for HNLs, which are heavier than, maybe I'll come somewhere here, for example. If you look for HNLs, which are heavier than 2 GeV, they need to come from B decays. And B decays, we don't have really any useful cross-section with the 120 GeV B beam. That's why SHIP goes to 400 GeV. And then you get a decent B cross-section in there, which you can use. And that is what makes the difference, for example, between where we stop here and where SHIP can go. Whoops, yeah, where SHIP can go. 2 GeV we stop, and where SHIP can go. So that's one extent. We cannot go to higher masses because we don't have the heavier resonances in there. In fact, the CMS and Atlas look in here, they look at neutrinos coming from W's and Z's eventually with the FCC, for example, and that can bring it in that direction. In this direction, going down to lower couplings, that has two aspects. That's a matter of rate, but also a matter of where your detector is. The point is that if you want to measure more in this region here and bring that down, for example, or in this one here and bring that down, the detector is not at an optimal place. The decay length of where that happens is you see a too small fraction of that. So you would maybe even want to have then two near detectors, one at different distances for covering more of that phase space. On the quality of the detector, I don't think there is something specific that we haven't actually, I would put it differently. We haven't hit the wall of the detector yet. It's really event rate that we get of the decays which are going in that detector. And it's not the material, nothing, it's just decays. So that is what limiting us. So that's for that. And for the first thing you said, I'm totally happy that we are trying to push more on the far detector for getting going to lower thresholds, for example, if possible. I think now I think 5 MeV is already something that seems feasible in some circumstances. We use something higher in our studies because that will also increase the phase space of the searches for dark matter that we can do. The far detector is not so useful for HNLs. I hope that answered the question.
Yeah, sure, Albert. Thanks.
And then there's another question from Jose.
Hi, Albert. Can you hear me?
Sure.
Okay. Thank you very much for the very nice seminar. Precisely on this slide, I have a question about the Big Bang nucleosynthesis bound that you commented is dynamic. Can you give us more details about like how can it be moved and what it depends on?
What is dynamic is the following. So this is actually for a particular kind of interaction. I didn't push that detail, but what you have here is that you have no mixing with other generations than, for example, the electron neutrino here. And that gives this mystical thing here, which saying that the 1, 0, 0. So it's all coupling to the electron neutrino, all mixing to the electron neutrino. Sorry, I should say it like that. Now, that's a choice. And at the moment, you start adding in possibilities that there could be also mixing in the muons or mixing even to the taus. You can change this BBN prediction quite a bit. And in that sense, I mean, the measurement would remain still what it is largely. Maybe you have a bit of loss in this channel because 10% goes to the muons and only 90% to the electrons. So you may have a little bit of loss, but for the measurement you're going to do, if you find something, but here for the BBN limits, that there is an effect there, and in that sense, that is more stringent. While the seesaw is really having to cover all the 3 generations in a uniform way. That's not so movable. So in that sense, it depends. This plot is exactly done for this condition here for these predictions which we have.
Thank you.
All right.
And another question from Begoña.
Yes, here, Begoña. Hello, Albert. A CMS colleague of yours. So
yes, of course. I'm still CMS, so yeah.
Yeah, sure.
Right.
But I am very glad to listen to you in this context also. So as you were mentioning, Dune will provide results in basically in the low mass region for many of the items and topics you have been presenting, and this is nicely complementing the searches at the LHC. But you were also saying that these results will come mainly around 30 something, 35, 33. So in a few years from now, and run 3 will be by then done, and results will be out from the LHC. So probably what you have been showing now are the current limits by CMS and Atlas, but the projections for that time, for the end of run 3, will probably move towards a bit lower masses and lower couplings, maybe not reaching totally, of course, the
right.
But
well, I can indicate you what's gonna happen.
Yes.
Because I work myself on HNL analysis in CMS, so well, yeah. I mean my students. I'm not. I'm only talking about it. But so what's gonna happen here is that this is not gonna I mean, look at the scale. This is like an order of magnitude. You see here. So these are not going to get better by an order of magnitude like that, because we have already the results here, which are for like 30 inverse femtobarn for the 2016 data. And at the end of run 3, which is in 2024, we're going to have 300. So even if you have a 0 background things, you're going to be better, like not, well, maximum an order of magnitude better here. What we're going to do and what we're working on in CMS actually is this region here, because this is prompt. This is actually looking for prompt, but here they are long-lived and they decay in the tracker. And this is what we're doing now. So we will fill in this corner and we come probably a bit lower than that. Oops, starting to move the figure. Become a bit lower than that, but that will not be in competition with what this Dune experiment is going to do here. What the high luminosity is going to bring, that's another factor of 10 in luminosity. Well, it will bring it, of course, further down, but I see that this Dune measurements are more going to be in competition, or not in competition, in complementary with what we're going to see at the time of 2035 or something like that, from the LHC. Because also the experiments you see here, the other experiments like SHIP and Methuselah, which maybe I mentioned this a bit, you can see it better. SHIP and Methuselah, they are actually not experiments that are going to run any sooner than Dune or the phase 2 of the LHC. So this is really looking 10, 15 years in the future.
Mm-hmm. Yeah, this is true. Thanks.
And one thing I could actually say, I skipped it, but I have an idea to look for this dark matter, for example, to start already next year, but with the Icarus experiment and using a 120 GeV beam, looking for this light dark matter type of objects in Icarus. And it actually gives us something that will be coming sooner. This is not for HNLs. This is for the, well, we're going to study also what the HNLs, what we can do, but this is for dark matter. So we will have in the next years more and more results also from the present experiments, which are getting online now, like Icarus, or are there on some of these topics to see progress. But what I showed on that slide, you should think of like 15 years from now. The slide before.
Okay, so thanks.
I don't see any other hands. So yeah, no more questions. Then let me thank you once more for the nice seminar. It's clear that Dune has many possibilities to discover new physics in the next years. Once again, we wish we could have you at CIEMAT soon.
Hopefully there comes a day. All right. Okay.
Bye.
My pleasure.
And thanks to all of
and
you.
If you're
for
interested, I don't know, maybe you would like to store the talk somewhere, then I will send it to you. But if some people are interested in something, they can always contact me. If they, I mean, someone in the group there, they know me very well, so that you can contact the locals also. And
yeah, and yes, but sure, please send us the slides because we will post them in the Indico page with the recording.
All right.
Bye, and thanks to all of you for attending. See you.